It started. Anyway, yeah, it's fun. Okay, so I know we're deep in the thick of Spinors, and they're kind of ugly and they're kind of new, but at the end of this story, we'll kind of finish it up with my very bad spelling of a word. But we'll get there in due time. It's kind of a funny, it's not really a story, it's just a funny anecdote about me and my inability to spell. But anyway, we'll get there. Okay, so I just want to very quickly review what we where we ended up last time, and then we'll finish that story today. So recall the map in transforming a spinor with basically the spinorial version of a coordinate transformation is given by e to the I over 4 sigma mu nu omega mu nu acting on the spinor, where the sigma mu nu's, so I'm going to just put this in a bit of bracket. It's an important fundamental degree to the story, where the sigma mu nu's are defined as the set minus I over 4 commutator gamma 0 gamma 1 minus I over 4 commutator gamma 0 gamma 2, etc. Okay. So basically, we have 6 of these. We have 6 of these generators, and we had this problem last time because if we just tried to say that it was a gamma, there's only 4 gammas, but there are supposed to be 6 generators of SO1, 3. So what we realized was instead of using a single gamma, we could instead use the result of the Lie algebra, which gave us pairs, and then there are 6 pairs of 4 gammas. You take if you have 4 things and you can pick pairs where the 2 elements are distinct from each other, there are 6 possibilities, okay? And obviously the sigma mu nu sigma 0, 1 is equal to minus sigma 1, 0, because switching 0 and 1 is just flipping the commutator, which gives you a negative sign. And also the parameters, the omega mu nu's are the parameters of the transformation. So this is the usual exponential map. This is the generators. These are the parameters of the transformation. And these can all be written as 4x4 matrices because the sigma mu nu's are 4x4 matrices. So the exponential map will give you a 4x4 matrix in the end, and it acts on this 4-component spinor. So this is a very consistent story. Just be aware, and I'll reiterate this. Even though these spinors have 4 components, their 4 components are not affiliated with the 4 components of a vector. A vector has a time component, an x component, a y component, a z component. Spinors do not have those components. So the fact that both of them have 4 components make you think that they're very similar. They're not. They're very different. However, what I want to, and I'll go over this again later, what I want to reiterate to you is that spinors are just a different version of things which transform under coordinate transformations. So if in our theory we have vectors and spinors, and we do a coordinate transformation, both the vectors and the spinors transform. The vectors transform in the usual manner, which we've talked about, and we'll go over that again later, but the spinors transform in this way. But if you do a coordinate transformation, it transforms both vectors and spinors, okay? It just transforms them in wildly different ways. We'll go over that more in detail. So I also gave you a set of the gammas. Let me very quickly remind you this one's dying, so I'll toss it. Hopefully these aren't all 3 dying. That would be like the beginning of our last class where everything just hit the fan. Gamma 0 is minus I 0, identity, identity 0. Where this is a 4x4 matrix, every element is a 2x2 matrix. It's just a concise notation. I'm not going to write down the elements of 4x4 matrices. And then the spatial parts are minus I sigma I minus sigma I0, where the sigma i's are sigma 1 is 0, 1, 1, 0, sigma 2 is 0 minus I0, and sigma 3 is 1, 0, 0, minus 1. Notice all of these sigmas enjoy the property that sigma dagger equals sigma. Okay, that is, if you transpose and complex conjugate, you get the same thing you started with back. Okay. Now we can actually form what these generators look like since we're given the gammas. So let's actually do that. So we'll start with the sigma 0I. That is, this is the one where we take mu to be 0, and then we take the second index to be any I. Okay? What about sigma 0, 0? Caleb? I'm going straight to sigma 0I. What about sigma 0, 0?
Say the beginning again.
I'm starting out with going to sigma 0I, where 0 is the time index and I is the spatial index. Why don't I start out with time and time indices?
I'm not sure, because you can't generate time twice.
Say again?
You can't generate time twice.
Well, it's actually more mathematical than that. That's a deep physical reasoning, but it's actually more mathematical than that. Anybody want to help them?
The commutator is 0.
Yeah, so remember the sigma mu nu is defined as the commutator. So if I do 0, 1, I use the commutator of gamma 0 and gamma 1. Well, if I tried 0, 0, I would be doing the commutator of gamma 0 with gamma 0, and what's that? It's 0 automatically. Because if I multiply gamma 0, and then subtract reversing their order, it's 0. Okay, so we're going to skip sigma 0, 0 and go straight to sigma 0I. So this, of course, is minus I over 4, commutator of gamma 0, gamma I. And you could crank this out. I mean, I'm not doing anything magical here. This is just matrix multiplication. And in the end, and I have the details in my notes, but in the end, this is going to give me I over 2, sigma I 0, 0, minus sigma I. Okay? So the factor of 4 here is actually useful because when we do this commutator to find the generators, what we find is I over 2 times sigma I in the upper left and minus sigma I in the lower right. Okay? And what you may or may not remember is that, first of all, this thing can act on a psi, which has 4 components. Psi 1, psi 2, psi 3, psi 4. Okay? But notice, this piece is only going to transform the first two, and this piece is only going to transform the second, or the third and fourth terms, right? You got 0 in the places where you can mix the first 2 and the last 2, all right? Now, sigma I entered our story earlier, didn't it? Weren't these the Pauli matrices? They were related to the generators of SU2. Well, what we're finding is that now that we have a sigma I acting on the first 2 and a sigma I acting on the second 2, and this is the I over 2 that we used in that case, what we're discovering is that we have SU2 on the first 2 components and then a separate SU2 on the second 2 components. Okay? So that's what this is sort of generating. And then we have the sigma ij's, which is of course minus I over 4 gamma I gamma j. And this turns out to be 1/2 epsilon I j k sigma k 0, 0 sigma k. Where as an example, we can do sigma 1, 2, which gives me 1/2 sigma 3, 0, 0 sigma 3. Okay? again, even though it, go ahead, sir.
After the E, I, J, epsilon, I, J, K, is that sigma mu?
Sigma K. And don't get me wrong, even though it looks like everything I'm writing is 2 by 2 matrices, they're all 4 by 4 matrices. Because these are 2 by 2 matrices inside of this, so it's a 4 by 4. It's just, it's easier to write it this way. And it's more natural because you're just basically saying, this is an SU2, this is an SU2, and then it follows all that SU2 garbage that we've already looked at. Okay. All right, so now that we've got an idea of how these spinors transform, you use the exponential map with the generators and the parameters, where now we have at least an idea of what the generators look like. They just look like the generators of SU2 across SU2. Remember, that's how we organized. We took the rotation generators, the K and the J's, and we realized that they don't actually, the J's, the angular momentum generators, form a subgroup, but the K's don't, because if you do a J and a K commutator, you get back something. But anyway, that's not zero. But anyway, we reorganized them in terms of plus and minus, and then we found that they broke into 2 different groups, 2 factors of SU2, and that's how we define these. So here it's just playing out in this realization. Now, of course, now that we know how these spinors transform, what we want to do is we want to build invariants. So let's talk a little bit about what an invariant would look like. So, okay, so last time we said, well, first of all, the standard invariant is that you form the dual, and then you complex conjugate and transpose that, because these are imaginary. And ideally, this would be an invariant. Okay? And we can try what we discovered for the 3-dimensional 2-component spinors. That's, remember, in 3 dimensions, the spinors only have 2 components. We can try what we discovered with those, which was that the duals actually have the same components as the original spinor. Okay, we discovered that for the 2-dimensional version of 3-dimensional rotations. So we'll try that in this case, and we'll see where it fails. So let's say psi twiddle dagger psi is just psi dagger psi. That's saying, okay, this is the standard invariant, but we're going to use this property, so I'm just going to replace the psi twiddle with psi. And then we can ask, what does this do under a transformation? Okay. And ideally, if this works, then we're going to get back what we started with. However, we're not. So let's write down how these transform. So this is e to the I over 4 sigma mu nu omega mu nu times psi dagger. E to the I over 4 sigma mu nu omega mu nu times psi. Okay. Now, once again, and this is a step that we've done a gazillion times, so hopefully it doesn't seem too magical or mysterious to you. We have the Hermitian conjugate of the product of 2 things, and we would like to make that the Hermitian conjugate of each of them, but that means you have to switch the order. Okay, so this is going to be psi dagger, and then, and I'm going to write it like this, e to the I over 4 sigma mu nu omega mu nu dagger e to the I over 4 sigma mu nu omega mu nu times psi. Okay? Now, let's pause. We had a very similar expression in the 2-dimensional spinors associated with 3-dimensional case. And what we observed was, and in that story it was e to the I over 2 sigma, sigma dot alpha, where these are the Pauli matrices and these are the perimeters. And we daggered that, and then it was e to the I over 2 sigma I alpha I, and then a psi dagger and a psi, okay? And in the 2-dimensional version, what we discovered is that all of the Pauli matrices here are Hermitian. That's what I told you. Okay? So Hermitian conjugating these gives you back these. These are just parameters, real parameters. So the only impact of this Hermitian conjugation is that it puts an I, it puts a negative in front of this I. Okay? That's from the complex conjugation. But that means that this thing basically becomes this, and these combine to give you the identity. And therefore we get back psi dagger psi. Okay? That's the SU2 story. Now I want you to look really carefully. Where does that go wrong?
The time and space, the time and space transformation with the minus, yeah.
Exactly. This guy, if I dagger him, these are not going to change, but that's going to pick up a minus. So what we find is that sigma 0 I dagger is minus sigma 0 I. However, sigma ij dagger is sigma ij. So these are not behaving in the same way. So this, of course, is a sum over all of them, but that means that I get a minus on some, 3 of them in fact, just taking 1, 2, and 3, and then I get plus on the others. So there's no way that this can cancel that. Maybe if I was getting a minus on all of them, then it would definitely cancel. Or if I was getting a plus, I could just somehow throw in a minus or something, I don't know. But it's just not gonna work out, all right? So we'll have to fix it. Okay? Turns out fixing it is not that hard. In order to fix it, here's what we're gonna do. And I guess I'm gonna rewrite all this again. Yeah, I am, shoot. Okay, so we're gonna give it that try. And again, that whole story that psi dagger or psi twiddle, the dual of psi was equal to psi, is based on the idea that G is the identity. Because remember, you build duals by applying G to the original. Okay? So what we're going to do is we're going to change our approach, and we're going to say, okay, suppose that instead I multiply by I, and I act with the gamma 0 matrix. Okay? I act with this thing. So this is going to be how I find the dual spinor, starting with a spinor. I hit it with gamma 0. And I just want to remind you, this is a spinor. It lives in spin space, and this is a matrix in spin space. Okay, the fact that this is a matrix has nothing to do with space-time. It's got to do with spin space. This is a 4x4 matrix in spin space. And I'll say more about that in a bit. Okay, but this is just the way that we're going to do this. Now let's see how this works out. Psi twiddle psi is, of course, I gamma 0 psi dagger psi. It's just replacing the psi twiddle with I gamma 0 psi. Okay. Now I can go ahead and dagger this. So this is going to be minus I psi dagger gamma 0 dagger. Okay, again, the I is just a number, it comes out. This is the product of two things. If I'm going to do the Hermitian conjugate, I have to of each of them, then I have to reverse them. Okay. And then, of course, we have the gamma 0 dagger is what? What is it?
4x4, then it becomes I.
So I'm just daggering this.
Oh.
So I'm transposing,
Negative gamma.
and then I get, yeah, it's negative gamma 0. Does that make sense? Does everybody follow that? The dagger is just transpose and complex conjugate. Transposing these doesn't do anything. Complex conjugating throws a minus there. Okay? So this is going to pick up a minus, and otherwise it's going to be gamma 0. Of course, that minus will cancel with this, so this is going to be psi dagger gamma 0 psi. Okay? Now, this is just cleaning up this expression using this definition. Now we're going to transform it. and ask, do I get the same thing that I started with back? So now we want to send this to I, psi prime dagger, gamma 0, psi prime. And now we can use the transformations. So I, e to the I over 4, sigma mu nu, omega mu nu, psi, dagger, gamma 0, e to the I over 4, sigma mu nu, omega mu nu, times psi. Okay? And then once again, this is the product of two things daggered, so I can reduce it to this. Okay? And now here is the magic. This thing right here actually gives you e to the minus I over 4 sigma mu nu, omega mu nu. Okay? So notice what happened. In evaluating this, you can actually swap the gamma 0 to the other side, but in doing that, you pick up a minus, and this is with the transpose enacted, okay? Now, that might look a little confusing. That's why you're gonna work it on your homework. Okay? Really and truthfully, all you're gonna do is you're gonna consider how the dagger treats some of the sigmas differently. Remember what we said? Okay, daggering gamma 0I gives you a minus, whereas daggering gamma ij doesn't. However, also moving the gamma 0 past this, it treats them differently. In a way such that the combination of daggering and moving gamma 0 to the other side, it treats everything exactly the same. Okay, you'll get this in the details of your homework, okay? But of course, what is useful to see now is that, what are these? Any takers? The identity. So we end up with I, sigma dagger, gamma 0 psi, which is exactly what we started with. Okay? So again, in your homework, you're going to basically show that this gives you this. All right? And again, it's due to the cancellation of two effects, both of which treat things differently, but in combination, they treat everything the same. Okay? All right. So the notation here is getting ugly. So here's what we're going to say. We're going to call gamma twiddle dagger, which is of course I psi dagger gamma 0. Okay, I mean if I just dagger this, I'm daggering this whole thing, which is going to, yeah, so it's going to end up, if I reverse the order, it's going to be I psi dagger gamma 0 dagger. The gamma 0 dagger is going to just pick up a minus sign, and you're going to get a minus sign from this I, and they're going to cancel. That's what you're left with. Since this is going to be used so often, we're just going to call this psi bar. And psi bar is the notation we'll use henceforth. So basically, psi bar is the very useful dual to a Spinor psi. Okay? All right. Now is where we're going to get away from this gross notation, and I'm going to tell you how this story plays out in our calculations, because it's actually much cleaner than what you've been seeing. This is very nitty-gritty, but this is actually, it's kind of run-of-the-mill in particle physics. We take really nitty-gritty stuff and then we just smooth it over like butter. And we say, we'll just ignore that, we'll just call it this and we're done, okay? So let's carry on. Now we have an invariant. Notice psi dagger psi is an invariant. Okay? Or sorry, not psi dagger, psi bar psi is an invariant. So this of course means that we can build a Lagrangian and include spinors in it, which transform non-trivially. However, we have a way to build invariants because our Lagrangian has always got to be an invariant. Okay, so you need a means of building invariants out of these transforming spinors. Well, this is a simple way to do it. We're going to find a more interesting way in just a moment. But I want to just sort of pause for a moment and have a discussion with you about these gamma matrices. Because the gamma matrices, obviously, you know, they play this very important role in constructing these generators. However, the gamma matrices, I just kind of want to give you an idea of the role that they play. So first of all, a gamma matrix secretly has these two little subindices, and these indices go over the spinor components. Spinors have 4 components. This is a matrix, so it has to have 2 indices. And the 2 indices that we never write, we never put these go over the spinor components. These are space-time vector components. This goes over T, X, Y, Z. These go over the 4 spinor components. So if you think about it, the gamma matrices sort of form a bridge between these 2 different sort of aspects of space. There's the vector description that's captured by the mu, and then there's the spinor description, which is captured by the AB. Please note, this, while it is a matrix in spin space, it is a vector in space-time. That makes sense? It's got a single index for space-time, and that's indicative of a vector, whereas this tells you it's a matrix in spin space. Okay? But nonetheless, these gammas are very special because they carry both vector, space-time vector, and spinor indices. So they're sort of a way of talking between these 2. Okay? Now, I don't think I told you guys this, but I'm going to tell you this very quickly. Where do vectors live? I need to ask this. Sam, you should know the answer to this. Where do vectors live?
Space-time?
No. It's close. Where do vectors? I mean, I know I've been saying vectors in space-time and all that stuff, but technically, where do vectors live?
Is it the tangent space?
Yeah, it's in the tangent space to a space-time. Have I already gone over this with you all? I mentioned it. Well, it's a super simple point. Like if you're in flat space, like R2, then you can imagine vectors just live in R2 because, you know, R2 is the space you use to define vectors. But then I just ask you, what if you live on the surface of the sphere? Do vectors point along the sphere? Hell no, they don't. Because if you try and take 2 vectors along the sphere and define addition, it's just stupid. You can't do it. Okay? So in order to define vectors, we don't have vectors in space. Like they don't point from this point to that point. The position vector is just a bullshit notion that you were introduced to in calculus and you never should have been. So forget about the position vector. Let's talk about real vectors like velocity, acceleration, force. Those things do not extend from this point to that point. You know, your velocity doesn't go from this point in space to that point. No, your velocity is defined where you are, only at that point. But at any rate, this is just the rigorous definition. What we do is we say you take the space, and at each point, you define what's called the tangent space at that point. And notice for a curved surface, the tangents point different directions as you move around. Then the vectors at this point all live in this tangent space. Similarly, the vectors at this point all live in this tangent space, okay? So you have a space-time, and yeah, in this class, the space-time is flat, so we really don't need this curvature argument, but that's gonna help with what I'm about to say. The fact that vectors have to live in this tangent space, and this is technically called a tangent bundle, It's a bundle of these tangent spaces, so it's called a tangent bundle. You might ask, where the hell do spinors live? First of all, remember, a tangent space has got the same dimensionality as the underlying space. It's just the tangent lines through this point. Well, spinors live in what is called the spin bundle. And the spin bundle at each point is once again a four-dimensional space, except these do not come from just drawing the tangents through the point. Okay? But this is the important observation. We have space-time, upon which neither vectors nor spinors live, but rather we have the tangent spaces where the vectors live, and then we also have the spinor spaces, which is altogether called the spin bundle. And it's in those spin spaces where the spinors live. Okay? What's important is the bundles are intimately tied to the geometry. So if I do a coordinate transformation on this surface, I will impact both the tangent spaces and the spin spaces. That's why both vectors and spinors transform if you do a coordinate transformation. Okay? That make sense? Kind of. I mean, I do go over that in a bit more detail in my GR class, but I just wanted to make that point. Now, to relax a bit and ease on our notation, let me go ahead and make a definition for you. What we'll do is we'll say the following. We're going to call this, and let me just come up and say a bit more. So first of all, remember how vector transformations were defined. Okay. And this marker's dying too. All right. So these are the transformations of vectors. If I do a transformation on the space, if there's a coordinate transformation, that transforms all the vectors, and it transforms all the spinors. Okay? So the way that we can notate this is we can say, this transformation is the spinor version of whatever the lambda is I'm doing here. Okay? So, you know, we can define the coordinate transformation in terms of how it acts on vectors. That's super easy, okay? Because we got rotations and boosts. Every single one of them has a corresponding element that acts in spin space. So I can call that the spinor representation of the coordinate transformation. That's just, you know, S of lambda. And so if you pick a lambda, you can write down the corresponding S. This is just a notation-friendly thing. Okay. Now, gamma mu is a vector. Now, so far as I've told you, I have resisted indexing the spinors and the spin operators. The psi has no index, even though it's got 4 components. This is the one time in the entire story where I will give them indices, just to prove a point, okay? So let me argue that the spinor with an index A, which takes 4 values, they are not t, x, y, z, they are the spinor values, okay? So we're going to say that it transforms into a new form through the action of the spinor version of whatever transformation lambda we're picking. Okay? And moreover, psi b transforms as S lambda b b prime psi bar b. Okay? And then for psi bar a, psi a to be invariant, we need psi bar a, psi a goes to psi bar a prime, psi a prime, which is, of course, psi bar a S lambda A prime, S lambda A prime B psi B. And we need this to be the identity. Okay? So if we call the spin transformation associated with lambda with indices A prime and A, these are the ones in this transformation. If we call this just S lambda, then this guy is just going to be S lambda inverse. Okay, so it plays out the same way that we did with the lambdas. All right? Now, the reason why I'm showing you that is as follows, and this is where it gets interesting. All right. So first of all, with these spinor indices, gamma mu becomes gamma mu A B, okay? And then what we can say is, all right, if I take psi bar A, gamma mu A B, psi B, okay? Then this will obviously make sense with the Einstein summation convention. And to figure out, we know how these transform, so to figure out how this gamma transforms, we just transform every index that it has. It has a vector and spinor indices. So if we want to transform this, we say, okay, this goes to gamma mu prime, A prime, B prime. And this is going to be lambda mu prime mu, S lambda, A prime A, S lambda, B B prime, gamma mu A B, okay? And then we can write that as lambda mu prime mu, S lambda, A prime A, gamma mu A B, S lambda, B B prime. Okay? Now, if we ignore the spinor indices on it, then this is just lambda mu prime mu, S lambda, gamma mu, S lambda inverse. Okay? So, the gamma mu's, they're non-trivial in space-time and they're non-trivial in spin space. So if I do a coordinate transformation, the vector index transforms according to the vector rule, and the two spinor indices transform according to the spinor rule. Okay? So looking at that gamma, you might think to yourself, wow, what a pain in the ass. It's basically got three indices and you have to transform all of them. Two of them in spinor language, one of them in vector language. That's crazy, right? Right? Here's the beautiful part of the story. You can basically ignore the spinor transformations in everything you do. How and why in the world can you do that? Well, it's really simple. And this is where I can't spell worth shit. It turns out that anytime gamma mu appears, it lies, I'm going to write it anyway, inside of what is often called a spinor sandwich. And what's hilarious is I apparently grew up misspelling the word sandwich, and I was only corrected about 4 years ago. So I made it well into my 40s not knowing how to spell sandwich. So I'm just going to stick with my old spelling of sandwich. But anyway, in all honesty, these things are always going to sit in a spinner sandwich. Now, what the hell do you think a spinner sandwich has? What do you think the bread of a spinner sandwich is? It's a sandwich. You got stuff between two slices of bread. What are the slices of bread in a spinner sandwich?
Dual and regular spinner.
Yeah, it's a dual and a regular spinner. And then this is the meat and cheese and hummus and ketchup. Anyway, that's where all the stuff lies. Why would we always work with spinner sandwiches?
It'll undo the spinner transformations you got there, right?
Say it again?
It'll undo the spinner transformations.
Right, but yes, exactly. Okay, so let me just show you why it's going to work. So if I consider, if I consider a spinner sandwich with just gamma mu as the meat, okay, then this transforms to psi bar prime, gamma mu prime, psi prime, which is psi bar s lambda inverse. Okay, that's how psi bar transforms. Okay, psi bar prime just becomes psi bar s lambda inverse. And then the gamma mu transforms as s gamma lambda mu prime mu, gamma mu s lambda inverse. And then this psi prime is built from s lambda times psi. Okay? Now look at that. Identity, identity. So in the end, this transforms to psi bar lambda mu prime mu gamma mu psi. In fact, this is what's beautiful about it. This transformation does not care about spin space at all. This is a purely space-time thing. So it can come out of the spinner sandwich. It doesn't have to live inside of it. So this is basically lambda mu prime mu psi bar gamma mu psi. So what I'm saying is this thing right here is just a vector in space-time. It's not a spinner. It's invariant. Well, it is a spinner, but it's invariant under spin transformations because it's psi bar psi with stuff in between. Okay? Remember, psi bar psi is invariant. That's a scalar, even under the spinner transformations. This is a vector under all of the transformations because you get a lambda transformation and you get all these spin transformations, but all the spin transformations cancel. Okay?
How do we know that the lambda and the s lambda are, or that they commute, I guess? Because you had to do that to pull it out of the...
The lambda and the s lambda?
Yeah.
The s lambda, no, actually, no. The s lambdas, so these cancel to give the identity before I even move this out.
Well, when you wrote it before, it was...
Here?
Yeah, that was lambda, s lambda, and then the next line you put s lambda, lambda. So they commuted there.
Oh, I see what you mean. Yeah.
Is it just because they're not in the same space?
Yeah. No, that's it. Exactly. Yeah. It's because they're not in the same space. Okay? So, the bottom line in this story is that in this class, we will work explicitly with spinner sandwiches, where you don't even have to worry about transforming the spinners, because every spinner sandwich is a scalar in spin space. It's not a scalar in space-time. This is a scalar in space-time, but this is a vector. In fact, I can build a 2 tensor. Can do that as well. This will transform in exactly the same way as a 2-0 tensor. You'll just transform these vector indices. Okay? Yes?
If you like sandwich like an upper and a lower, would that make like a 1-1 tensor?
If I do,
Yeah, like a lower two.
well,
Or the
well, I mean, it depends. Like the gamma mu and the gamma nu only have upper indices, so you don't lower their indices. But I could always, you know, put in something with lower indices, you know, something like that. But this would just be a space-time tensor, and it would just come out of the spinor sandwich because it's purely space-time. But the overall thing here would transform like a 0-1 tensor actually, because I'm summing over the mu. But yeah, you can definitely, and we'll see that that's a part of the story later on. Okay. How do we feel about spinors? Kind of like, I haven't even written down what they look like yet. I've just said they're 4-component things and they get transformed in this way. But we will, in time, figure out exactly what they look like. They look very, very different from the spinors that you might have seen in non-relativistic quantum mechanics. In non-relativistic quantum mechanics, you just said, oh, I got chi plus or minus. This is either 1, 0, or 0, 1. Oh, Ross! Shoot. Oh, man. I thought it was one of those students hanging out. Okay, it turns out that in the relativistic story, it's a way more complicated thing, okay? So we have that to look forward to. But first and foremost, in order to get there, we have to write down the equation of motion that a spinor satisfies. Where are we going to get an equation of motion from? A Lagrangian. So we actually have to do some Lagrangian mechanics now. Okay? So now we're going to pause on spinors, not really, but we're going to pause on spinors, switch gears, and we're going to talk about Lagrangians and actions and equations of motion and so forth. And then we'll come back to integrating spinors into the story. Okay? So are there any subsequent questions about spinors before we move on? And again, the more you work with them, the more, they'll never be intuitive. Okay? No one claims to really understand what the hell a spinor is. We've got a lot of pretty mathematical descriptions, but no one is really, really certain what they are. Okay, they're not nearly as clear and concise as space-time vectors, but whatever. Okay, all right, so now we're going to pause and talk about actions. And I, of course, talk about actions because action principles are where we get Lagrange's equations. And it turns out actions themselves play various roles in physics above and beyond just a Lagrangian. Okay. This eraser sucks. I grabbed it because I squirted this stuff and used these. Maybe I'll try these. Are these better? No, they're no better. Okay, anyway. All right. So the Lagrangian formalism, so if you've taken intermediate mechanics, how many of you have taken intermediate mechanics? All of you, good. How many of you saw Lagrangians in intermediate mechanics? How many of you saw Hamiltonians in intermediate mechanics? Okay, good. You know about Lagrangians and Hamiltonians. That's good. In most of advanced theoretical physics, whereby I mean particle physics, string theory, all that, we use Lagrangians. We don't use Hamiltonians. Okay? Because it turns out, there's a couple of reasons. First of all, if you want to go relativistic, Lagrangian's a much cleaner way to go. Hamiltonian is an operator which is specifically tied to the time dimension. It's not really democratic among space and time. The Lagrangian is very democratic. Okay? Furthermore, transitioning it to a field theory is much easier. But also, the quantum version of this is a bit easier. So just so you know, if we're going from non-relativistic to relativistic, then the integral of the Lagrangian with respect to time changes. You can pick time as a special coordinate in non-relativistic physics. That's given. But in relativistic physics, time is just another dimension in this four-dimensional space-time. So clearly we have to generalize this, and the way we generalize it is we integrate the Lagrangian over 4 dimensions. That's time, x, y, and z, okay? So where our action in non-relativistic physics is the integral of the Lagrangian with respect to time, in relativistic physics it will be the integral of the Lagrangian with respect to d4x, okay? If you want to move from point particles to fields, which we're obviously going to want to do, we're going to want to define things in terms of fields, then what you do is you take the position degree of freedom. A particle has a position and it evolves with time, and that's the primary degree of freedom for a particle. If you know that, you can derive the velocity, acceleration, so forth and so on. And we are going to replace these with field degrees of freedom. That is, we're going to have a field which is defined in terms of where and when you are. Okay? And then last but not least, in moving from classical to quantum mechanics, we take the action principle, that the variation of the action, which of course in non-relativistic physics is the integral of the Lagrangian with respect to time, you take the variation of that and set it equal to 0, and this condition is what generates the Lagrange equations of motion, or the Lagrange equations of motion, okay? This is going to be replaced by this construction, where I'm integrating over the field degrees of freedom with a weight of e to the I over h bar times the action s. You might know what that might be. Any takers? Ross?
Functional integral.
Or the path integral. Yeah. Okay. So in one version of quantizing a field theory, using a path integral formalism is very, very intuitive. Okay. And there you go. There's the role of the action, S. Okay. But here's my favorite reason for playing around with actions. Okay. My favorite reason for playing around with actions is they make symmetries totally manifest. In Hamiltonian formalisms, less so, but working with actions, you just say the Lagrangian has to be invariant in order for something to be a symmetry. We're going to hammer on that in due time.
Sorry, that's e to the what?
E to the I over h bar times s, where s is the action. Now, I know I'm using these words, but I'm going to sort of dig into them a bit, and then we're going to work out what the actions are for the free particles or free fields. But first of all, the action is a functional which is a function of functions. How many of you are familiar with functionals? Got about half the room comfortable with functionals. That's fine. Okay, so for example, if we take a function, we might say, okay, I have a function of x, that's x squared, and then if you give me a value of x, say 2, then the function gives me back a number, okay? Whereas a functional might be something like, if the functional of f of x is defined as the integral from 0 to 1 of f of x dx, notice this is a function of functions. So you give me a function and this will return a number. So for example, if I say s of the function x squared, this is just going to be integral from 0 to 1 x squared dx, which is of course 1/3. Okay? So whereas functions take a number and give you back a number, functionals take a function and give you back a number. It's pretty straightforward, right? Okay? Now what makes the language of functionals and this interpretation so nice is that you can imagine extremizing a functional in the same way that you extremize functions. Right? If you want to extremize a function, you just say, I'll take the derivative with respect to x and I'll set it to 0. Okay? This tells you the value of x, which gives you the largest output. Similarly, if I have a functional, I can set the variation of the functional, sorry, s, with respect to the functions equal to 0. And this tells me which functions give me the largest or smallest output. Okay? This is, I'm using a different d because this is definitely a different derivative. Okay? All right. Now you should be familiar with at least one form of the action, that is the integral of the Lagrangian with respect to time, where the Lagrangian, written in terms of position and velocities, can be constructed as the kinetic energy minus the potential energy, then setting the variational derivative of the Lagrangian equal to 0. This, of course, gives me, if I actually do it, dl dq minus d by dt dl dq dot equals 0. And these are, of course, the Euler-Lagrange equations. All right? So you start with an action and you say, I want to extremize it. I want to set the variational derivative to 0. And then this usually gives you an equation of motion. Okay? And the motion described by this will be the motion which extremizes the action. That's an action principle. Okay? How many of you saw action principles in your intermediate mechanics course? Okay, good. Christine's doing her job. All right. So, I think I might stop there because this next page is actually going to require a critical step, which I don't want to go over very quickly. So are there any outstanding questions for anything that I went over today? All right, so what we're going to do next is we're going to actually ask, what does the Lagrangian for vectors, spinors, scalars, what do those Lagrangians look like? And that is going to be a critical starting point in our story. Now you might wonder, what does a Lagrangian look like? Well, it looks like t minus v. Well, it's not quite this simple. What we could call this is the degrees of freedom, and then these are the interactions. And what we're going to at first develop is the terms in the Lagrangian for scalars, spinors, and vectors, which describe their free motion as if there are no interactions. And then we're going to take that simple starting point, and we'll explore that in depth, and you'll come out with a wonderful understanding of what the hell the Dirac equation is, and the Procco equation, as well as the Klein-Gord equation. But we're going to take that as our starting point for generating interactions through the insistence of a symmetry. And this is my most favorite topic in this entire course period, is taking a free theory and simply demanding that it have a symmetry, and from that you get interactions. That's the story that's going to play out over the course of the next few weeks. All right? So come back and I'll tell you the story.